beta y times x. So the rate at which they get eaten, instead of being, or the bond here is alpha, the rate, but here the rate, or death rate, is proportional to the instantaneous population of the foxes, and therefore it's minus some beta y. Here, it's proportional to the population of the rabbits, how much food is available. So it's plus delta x times y. Delta is a constant, it's not an increment in x. Now you have a nonlinear system. Earlier it was purely linear with a critical point at the origin, but now it's nonlinear. And there's the possibility of more than one critical point. And as you can see, if you factor out x here, there's x dot is x times alpha minus beta y. And this is minus gamma times minus y times gamma minus delta x. So there's a possibility of another critical point at y equal to alpha over beta, x equal to gamma over delta. These are all positive constants, so there's one more critical point somewhere. The question is, what's the nature of this critical point? And now you have to linearize. So let's shift variables to the point gamma over delta, alpha over beta, to this point here, and linearize about that axis, keep first order terms, etc. And you discover without too much trouble that this system here is a center. This critical point is a center. So this hyperbolic point, saddle point, the trajectories would do this, but because this is a center and there's nothing else, they'll eventually come back to this. And there's a point of coexistence, non-trivial point of coexistence. This is the simplest population model you can think of. Millions of complications can be added to it. I'll mention a couple of them. But you can see now that all the trajectories are going to do this. It's no longer circles, it's some very complicated curve, but it's a closed curve, one can show that. There's a constant of the motion. It's a transcendental function of x and y. Interesting exercise to calculate it. In fact, it was very interesting to find out how Voltaire first found it. It was in the days before computers, right? 1921 or something like that. And what they did was called the searchline method. So the idea was that he took a ray out of the origin and showed that it intersected in exactly 2 points. And then they had a very complicated graphical method where you plotted x here, f of x here, y there, and g of y here, and then transferred points of intersection and solved the equation numerically to get these closed curves. Very ingenious thing, described in a book, a very classic old book, maybe one of the first books outside the old Soviet Union on nonlinear dynamics. It's a book called Nonlinear Differential Equation by a guy called Davies. Nonlinear differential equations. And he describes this historical way of doing things in the Volterra model, along with a lot of other things, many interesting things which are, this book has a lot of gems. For instance, here's one. There's a big chapter on curves of pursuit. Namely, you have some animal running along, and you have another animal chasing it. And the question is, what's the optimal path that the second animal should take in order to intersect or catch the first animal, etc. So there are very interesting locus problems and things like that, solving nonlinear differential equations, among other things. In the Soviet Union itself, there was a lot of work going on nonlinear differential equations, which became known to the West only in the 60s and 70s later on. They had a lot of these things discovered independently. So this is a center, that's a saddle point. And now it's easy to see that on the average, volume is preserved over this. Let me show you explicitly how. Let's put all these constants equal to 1 and look at what happens. So you have x dot is x times 1 minus y, and y dot is minus y times 1 minus x. So the point 1, 1 is a critical point, and it's a center. Now what's del dot f in this case? It's the derivative of this with respect to x. So it's 1 minus y minus 1 minus x, which is equal to x minus 1. which is not identically equal to 0. It's equal to 0 on the line x equal to y, but otherwise not so. So, on this line, del dot f is identically 0, and the phase trajectories look like this. Neighboring trajectories would look like this. So in this region, where y is bigger than x, the phase trajectories, actually there's contraction of volume. Whereas here, in this side, there's expansion of volume. So as this volume element goes round, it contracts and expands, but on the average over a cycle it's 0. The expansion rate is 0, or the contraction rate is 0. So in that sense, this should be called a conservative system. So the definition that del dot f must be identically 0 for a conservative system is a little too rigid. We should extend it to say that if there's periodic motion, then on the average over cycles, if the del dot f is 0, then I would say it's still a conservative system. More generally, if I don't even have periodic motion, but a long time average of the volume element says that asymptotically the rate of change is going to 0, I would still try to classify it as a conservative system, or close to it. Even if it were, you could adjust constants such that this would happen. Even if it were. Yeah, in general, yeah, in the most general case, this need not be so. It's really, strictly speaking, a dissipative system. I'm not saying that the volume element is identically 0. But I'm saying when you have periodic motion in general, then systems come back to themselves, right? Completely, all variables. So a neighboring, a little phase space element goes out, wanders around, doesn't distort itself too much, increases, shrinks, etc., and comes back to its old value. Then over a cycle, it must be equal to 0, full cycle, no matter how many dimensions there are. And I should really call this a conservative. Here in this example, you can make it even more dramatic. Let's change variables. Let's change variables to, let's put q equal to log p, q equal to log y, p equal to log x. Then I put it to you that these are Hamilton's equations. It's a Hamiltonian system, because the critical point in the QP plane, the critical point at the origin here, xy, log 0 is minus infinity, so this critical point goes away to minus infinity, but 1, 1, log 1 is 0, and it comes here. And there's a center, and you have a harmonic oscillator, at least close to the critical point. Far away from it, you don't. And what's the Hamiltonian in this case? Well, it depends on the constant of motion here. So what you have to do, and that's a homework problem for you, is to take these two equations and integrate. Find the constant of motion. After all, that is a closed curve, and it's some constant of the motion. So a hint, it's easier in those variables. It's easier in this variable to find the constant of the motion. And it's a very interesting Hamiltonian in this case. It's of the form e to the p minus p plus e to the q minus q. That's not the usual Hamiltonian with kinetic energy plus potential energy, but it's a Hamiltonian. And as you can see, apart from some constants, near p equal to 0, q equal to 0, the linear term cancels out, and you have the harmonic oscillator. So exactly the harmonic oscillator, p squared plus q squared. And then far away, of course, it becomes something else. So that's why I said close to it, these are circles or ellipses, but far away, they're sort of ovals of some crazy kind. And because of this possibility of change of variables, there's no doubt that this is a Hamiltonian system, that this is a conservative system. You can't always do this. Pardon me?
Locally for this problem, actually solve it.
Yeah, you can solve it. But the interesting homework problem. Take this full Hamiltonian and find the time period of motion, at least asymptotically. Find out how it depends on the energy. If it's a harmonic oscillator, the time period does not depend on the amplitude. In other words, it doesn't depend on the energy. But if it's a nonlinear system, then the time period depends on the energy. And it's an interesting exercise to ask, given this phase trajectory, this equation, it's an interesting exercise to ask, what's the time period? And then you can quantize it. do quantized video, semi-classical quantization. So some interesting results come out. So, by the way, one word here, if you increase the number of variables and you had 3, 4, etc., this sort of Lotka-Volterra model with some arbitrary constants here, you have a big matrix, and you have bilinear couplings, x, y, x, z, and things like that, then the system sometimes is integrable, sometimes has only periodic motion, sometimes is chaotic. So it can have very complicated behavior. The moment you have 3 or more variables, no general rules. Some cases are known to be solvable for special values of parameters, but in the general case, very little is known. There was a question. Not necessarily. Not necessarily. His question is, if you have a periodic motion, can you always transform it to a Hamiltonian system? So let me immediately give you an example where this would not work. In fact, that brings me to the idea of a center manifold. So let me look at this center manifold. I need to know what's the actual numbers. Right. So consider x dot. My memory is slipping, so I need to look at this piece of paper. So x dot is minus y dot is x. Yeah. So that's just a harmonic oscillator. The eigenvalues are plus or minus I. It's a harmonic oscillator. And you would say that the origin is a center. Now, I pointed out that when you have a center, linearization may not give you the true flow. It may be very unreliable. And let me show you how unreliable it can be. So, if the actual flow is this, suppose that's the actual flow. Nonlinear. All kinds of crazy nonlinear terms sitting here. It's a very simple artificial example, no doubt, but it will tell you what the problem is with the center manifold. Existence of a center manifold. The next I'll give you an example where it's not even unique. Now, if you were to linearize this and say, where are the critical points? It's clear the critical point is at 0, 0. Both these guys vanish. 0, 0 is a critical point. Then you come along and say, let me find the Jacobian matrix at the origin, and that's non-zero. That's a non-singular matrix because it's just these two terms are retained. So L in this problem equal to 0, minus 1, 1, 0 implies lambda 1, 2 equal to plus or minus I. Implies center. Yeah. So I'm very happy. I've linearized the problem. Now I say, oh, there's a center at the origin. And then far away there's some nonlinear terms, etc., etc. I don't care. But then you have to be very careful. If I look at the full flow, the existence of this x squared plus y squared here suggests to me that I should choose polar coordinates. So let's choose polar coordinates. R equal to square root of x squared plus y squared, which implies r squared is x squared plus y squared. So rr dot is xx dot plus y. We differentiate both sides with respect to time, the squaring to get this. And then the polar angle theta is tan inverse y over x. This would imply that theta dot is the derivative of this guy. So it's 1 over 1 plus y squared plus x squared. Derivative of this with respect to x, which is y dot over x minus y over x squared x dot. If I have it right. Which if I simplify is xy dot minus x dot y over x squared plus y squared. That's the way the polar angle changes, and the other follows this. So now let's find out what those quantities are here. Xx dot plus yy dot is rr dot, I multiply by x and multiply by y and add the 2, and these two terms cancel out. This gives me x squared, this gives me y squared, so it's r to the power 4, or r dot equal to r cubed. But that's always greater than 0 for all r greater than 0. So everywhere in the plane, except at the critical point, it's going away. So it's not a center. Because the center would imply that trajectories in that neighborhood remain in that neighborhood. But here it says the radial distance is increasing indefinitely. And it's going away. In fact, it's an unstable spiral because you can compute theta dot, and that in this example will be xy dot. So we multiply this by x, and then yx dot will be this with a minus sign. So you get only this term, that term cancels out, and the r squared cancels, so it's 1. So this means theta equal to theta naught plus t. So what does it say about the critical point at the origin? You can solve this equation. And it's clear that you have dr over r cubed. If you integrate, you get 1 over r squared equal to t on the right hand side. And there's a 1 over r naught something or the other. So it's clear immediately that in a finite time, the radius is going to become infinite. And since theta is increasing with time, it's clear that it's an outward spiral, an unstable spiral, going outwards and hitting infinity at a finite time because it's a nonlinear. And that's a very far cry from what linearization told you. It said it was a center. And it's completely nonsensical. It's wrong. Because these nonlinear terms have completely changed the situation. So this is one of the things you have to watch out for. When you have a center manifold, you've got to be very careful. Linearization may not give you a reliable result at all. Yeah, exactly. So it says linearization is not a reliable guide in the neighborhood of a center manifold. In this case, we have a completely wrong answer. A very simple artificial example, but you can see the problems inherently.
No, but in this Hamiltonian, in these equations, you could have added some linear terms so that the eigenvalues are non-zero.
Yeah, then of course you can linearize it. Yeah, that's the theorem, that's this theorem due to Hartmann, Roman theorem, which says that in the absence of a center manifold, linearization is a unique asymptotic description of the true manifolds, of the true flow, and uniquely so. In the presence of a center manifold, you have to take recourse to more sophisticated methods. Can't always rely on it. For the whole thing, no, there's no center manifold. In this problem, there's no center manifold at all. Doesn't exist. The linearized problem predicted a center manifold, but doesn't exist. Doesn't exist at all. It's only an unstable manifold throughout. And the non-uniqueness comes about in the following way. Let me give another example which will show you how non-unique this can be. You see, what we meant by tangent manifolds was the following. When you had a saddle point, for instance, this could be your stable manifold, this could be your unstable manifold. So this is what we could call WU, and this would be WS. And the so-called linearization gave you this eigendirection as the stable manifold, and it gave this tangent direction as the unstable manifold. So that's what is meant by tangent spaces. So the true manifolds could be curved, they would be in general, but these things, the tangent spaces, would be Euclidean. On the other hand, pardon me? Yeah, they are the true unstable manifolds. Namely, if you're on this initial condition, you are guaranteed to flow away. If you're on this, you're guaranteed to flow in. But infinitesimally close to this critical point, this tangent line is good enough. You're going to flow. So it's in this sense that these are tangent spaces. Now imagine this for higher dimensions.
Sir, just I am confused about one thing. In the previous problem, there is a center manifold in the problem.
Yes, there apparently is. There apparently is if you linearize the problem.
Yeah.
But the true flow does not have a center manifold.
Then when I should use the linearization theorem and when I should not, how can I feel that within the problem?
Whenever the linearization gives you a center manifold, you better go back and examine the full nonlinear. You can't rely on it. In fact, let's look at an even simpler example. Let's look at x dot equal to x squared, y dot equal to minus y. I mean, nothing could be simpler than this. They're uncoupled. These two fellows are uncoupled. Now, what does linearization give you? The first thing you will say is, this is not generic. The reason is that this function f of x comma y, a generic function near the critical point, would start with some constant which you can absorb, linear term, quadratic term, etc. etc. But here that linear term is missing, starts with a quadratic term. This is therefore a higher order critical point. It's a degenerate or higher order critical point. But it has more than that. Let me explain what a higher order critical point does. So it's clear the only critical point is 0, 0. That's very clear. The right hand side vector field vanishes only at that point. So here's x, here's y. What do the flow lines look like? This equation is easy to solve. You can decouple the two and write a solution immediately. But if you start with x equal to 0, y goes in. So that's the first thing you draw. If you start with y equal to 0 on the x-axis, you have x dot is x squared, so if you're here, x increases. If you're here, x dot is positive, so it's going towards 0. So it's again going this way. And that doesn't look like any of the critical points that we had earlier. From the left, it's going into the origin, from the right, it's going away from the origin. So it looks like an attractor from the left and a repeller from the right-hand side. So it looks very weird. And it's not a simple critical point at all. It's a degenerate or higher order critical point. So what people do is to say, this polynomial is not generic. It's starting with an x squared. So it should be unfolded. And you should find the germ of this polynomial. Now, how does x squared come about? And there's a very elaborate theory for this. In fact, it's all part of something called bifurcation theory. Earlier was called catastrophe theory. And now is part of something else called foliation theory. It's a special case of it is bifurcation. So mathematicians have gone wild on this. But what the basic idea is that if you ask you to give you a polynomial, give me a polynomial in x, it would be a very atypical polynomial to give me a polynomial in which there is no linear or quadratic term. Start with linear or constant term. You start with quadratic, it's not generic. You need accidents for the first two coefficients to vanish. So you unfold it and put in a linear term. So let's say that this thing really came about from a flow like x times x minus epsilon, y dot equal to minus 1. And I'm going to let epsilon go to 0. Now I'm fine, because this is equal to minus epsilon x plus x squared, and this follows minus 1. Now I know, because there's a linear term, there's a quadratic term, and the limit epsilon goes to 0, I'm going to get to this. This has unfolded this degenerate critical point into simple critical points. Because now what are the critical points? So here's x, here's y. This flow line still goes like this. Where are the critical points here? It's at x equal to 0 and x equal to epsilon. So there's one here and there's another here. What sort of critical point is the origin? Well, I must linearize. Near the origin, I must linearize. So, near 0, 0, x dot is minus epsilon x, y dot equal to minus 1. The two eigenvalues are minus epsilon and minus 1, both negative. So it's a stable, asymptotically stable node at this point. So this guy is asymptotically stable, and I know that the flow lines must therefore go in like that. Close to this. What happens on this side? What happens to this epsilon? Well, stability must be followed by instability always. and so on, because roughly speaking, these are all potential. You can look at this as derived from a potential. To bifurcation theory, you will see it. Then, if you have a maximum of a potential, you have an unstable equilibrium point. Maximum must be followed by minimum. You can't have two maxima next to each other. So they must alternate, and therefore, if this guy is asymptotically stable, that must be unstable. And it's not hard to show that if you linearize near the point x equal to epsilon, so put x minus epsilon equal to u or something like that, then this will become a saddle point. Then the flow lines look very different altogether. They will look like this. This is a saddle, so you do this. It will do this and flow into that point. Do this, flow into this point, and things would flow in because it's a stable, asymptotically stable. That's what the flow lines would look like. And when you make epsilon go to 0, this region collapses and you get that picture. These guys will go like this. So what would you call this critical point? It comes from the coalescence of a saddle point and a node. So what would you call it? Saddle node. Mathematicians are very little-minded people. Very little. Saddle node. Saddle node. A higher order critical. What we've done is to unfold it. You can now ask the more interesting question, what happens if epsilon were negative? After all, I have this parameter epsilon. I start with positive epsilon and move in the epsilon plane, epsilon space, to negative values. What would then happen? This would become x plus mod epsilon. This would remain as it is. And then it's not hard to see that if epsilon becomes negative, near the origin, you have a plus here, and you have a minus here. So you have two eigenvalues with opposite signs. Therefore, it becomes a saddle point. And the node becomes a stable node. So as you cross epsilon equal to 0, now we are ready to. In epsilon, in this parameter epsilon, we are ready to write down what are the critical points. The y is irrelevant. Y is always 0. There's always, in the bifurcation diagram, there's also a y. There's also an x here. But the y is irrelevant. It's always at the origin. So I might as well just look at this. Because y equal to 0 is always a critical point in this simple example. You're starting with 0 is always, x equal to 0 is always a critical point. On the other hand, there's another critical point at x equal to epsilon. And when epsilon is positive, as in this case, this guy is unstable. And the origin is stable. That's right. And when epsilon is negative, it's the other way about. So let's draw the line x equal to epsilon. This is the line x equal to 0. And I would like to write x critical point. So x CP. So always the critical line. For positive values of epsilon, the point at epsilon is a saddle point and therefore unstable. On the other hand, this guy was stable. So this is your stable root. And this is unstable, and conventionally one draws it with a dotted line. And you go across to negative values of epsilon, then this point becomes stable, and x equal to epsilon becomes an unstable saddle point. And you have what's called the simplest example of a bifurcation diagram. A bifurcation is a phenomenon where if you change a parameter infinitesimally across some threshold value, the dynamical behavior of the system changes qualitatively. So here, what was stable has become unstable, what was unstable has become stable. These two guys have exchanged stability. Therefore, this bifurcation is called an exchange of stability bifurcation. It's also called a transcritical bifurcation, but exchange of stability. That's all it is. It's a very simple example. This was a linear thing.